Hello, welcome to our presentation. Our topic is counting and pigeonhole principle, and our assignment submitted to Priyanka Mondal, our honorable teacher from Daffodil International University. First of all, I am going to introduce about my group members. I am Ashikur. There is another group member named Ashik. Also there is Muhammad Russell and another is Jahid. We are four group members for this presentation here, and I am the host for this presentation. Our topics is going to be for counting basic rules in details, the rules of sum and the rules of product, which is also known as combination rule of counting, and the permutations from counting. At last we will be discuss about some problems with solution, and then on part 2 we are going to discuss about pigeonhole principle in details, the inclusion exclusion principle, and at last we will be give some problems with execution. Let's get started from the counting basic rules in details. In our daily lives, many a times we need to find out the number of all possible outcomes for a series of events. Hope it sounds weird, but if I give some quotient as example for this particular counting basic, for instance, in how many ways can a panel of judges comprising of 6 men and 4 women be chosen among 50 men and 38 women? Another is how many different 10-letter PAN numbers can be generated such that the first 5 letters are capital alphabets, the next 4 are digits, and the last is again a capital letter. These types of portion are very critical for human understanding. For solving these problems, mathematical theory of counting are used, I can say, and counting mainly encompasses fundamental counting rule, the permutation rule and the combination rule, which is also known as rules of sum and rules of product. Well, let's get into the second topics, the rules of sum and the rules of product, which is also known as combination rule. The rule of sum and the rule of product are used to decompose difficult counting problems into simple problems. The rule of sum: if a sequence of tasks T1 to Tm can be done in W1 to Wm ways respectively, the condition is that no task can be performed simultaneously. Then the number of ways to do one of these tasks is W1 to Wm. If we consider two tasks A and B which are disjoint, then mathematically the set of A union B equal set of A plus set of B. This is the rule of sum. If I elaborate the rule of product, then we can find if a sequence of tasks T1 to Tm can be done in W1 to Wm respectively, and every task arrives after the occurrence of the previous task, then there are W1 to Wm ways to perform the task. Mathematically, if a task B arrives after a task A, then set of A into B equal set of A into set of B. Then we can discuss about the permutation, which is the third topic from part 1. A permutation is an arrangement of some elements in which order matters. In other words, a permutation is an ordered combination of elements. For example, from a set, by taking 2 at a time, all permutations are for S equal XYZ equal XY, YX, XZ, ZX, YZ and ZY. Well, that was for our counting basic in principle. Now I will just show up some problems with solution from counting. Suppose A boy lives at X and wants to go to school at Z. From his home X he has to first reach Y and then Y to Z. He may go to he may go X to Y by either 3 bus routes or 2 train routes. From there, he can either choose 4 bus routes or 5 train routes to reach Z. How many ways are there to go from X to Z? If this is the question, then the solution will be from X to Y, he can go in 3 plus 2, which is rules of the sum. In this mathematical counting, then we can find 5. Thereafter he can go Y to Z in 4 plus 5, which is 9 ways. This is also the rule of sum, because in here he may go through 3 bus routes or 2 train routes. This is that equation, and from there he can either choose 4 bus routes or 5 train routes to reach. Then we combine that. At last, we just permute the, it's not permute, it's into, we just put down the 5 into 9, which is 45 ways. This is the rule of product. This is called also the combination rule for counting. On here, the combination of rule of sum. Here we are going to find a rule of product. That's why it's called the combination rule for counting. If we look upon the permutation section from problem 1, a bunch of 6 different cards. How many ways we can permute it? So as we know, permute will be just as like giving that variable as value, and of course that variable power will be the same value. As we are taking 6 cards at a time from a deck of 6 cards, the permutation will be 6p6 equals 720. If we look at the another problem, in how many ways can the letters of our reader be arranged? This is sound very easy, but if you think about use, something like there are more than 200 or 400 words and we need to solve that problem, then these permutations will be work. In if I add some words from my opinion, these discrete mathematics are going to open up the magic mullet for programming, and this is future, because on future will be very lazy and all programmable tasks will be done over artificial intelligence, where this discrete math will be very popular, because without logic building section you cannot build a huge program. Whatever, I don't want to enlarge the video. Let's get into the solution. There are 6 letters word: 2e, 1a, 1d and 2r in the word reader. Oh, that's so much easy, huh? Well, let's get into our part 2 topics, which is pigeonhole principle in details. If I told a story, in 1834, German mathematician Peter Gustav Lejeune Dirichlet stated a principle which he called the drawer principle. Now it is known as the pigeonhole principle. If I say something more about pigeonhole principle, which states that if there are fewer pigeonholes than total number of pigeon and each pigeon is put in a pigeonhole, then there must be at least one pigeonhole with more than one pigeon. If n pigeons are put into m pigeonholes where n is greater than m, there is a hole with more than one pigeon. Our next topics will be the inclusion and exclusion principle. The inclusion exclusion principle computes the cardinal number of the union of multiple non-disjoint sets. For two sets A and B, the principle states this equation. For these three sets A, B, C, the principle states this equation. Well, let's get into some problems with execution from pigeonhole. How many integers from 1 to 50 are multiples of 2 or 3 but not both? If I look upon the solution, from 1 to 100 there are 50 by 2 equal to 25 numbers which are multiples of 2. There are 50 by 3 equals 16 numbers which are multiples of 3. There are 50 by 6 equal 8 numbers which are multiples of both 2 and 3. So set of A equal 25, set of B equal 16, and A whatever is said union set equal 8. So from this equation we can get 25 plus 16 minus 8 equal 33. On problem 2, in a group of 50 students, 24 like cold drinks and 36 like hot drinks, and each student like at least one of the two drinks. How many like both coffee and tea? Solution: let X be the set of students who liked cold drinks and Y be the set of people who like hot drinks. So X union Y equal 50, set of X equal 24, set of Y equal 36. If I apply this equation, then the result will be 10. Hence, there are 10 students who like both tea and coffee. Okay, that was from our presentation. Thank you.